This is a dramatic reading of Quaternions for third graders, a blog by the stand-up physicist, available at science2.0.com. Third graders enjoy clay and pipe cleaners. Now, it might be a little cruel to give them graduate level graph theory that most math PhDs have never seen, but I might be able to get away with it if I use the right supplies from a craft store. You know, just tell kids that spinach is good for them. Well, children are right to be skeptical of me, as I expect of my viewers. Real numbers are just the most important numbers out there, bar none. Even for those math PhDs working in category theory can have Elmo count their functors so long as they write them on a piece of paper. Now, I have watched Elmo count 4 ducks, 4 birds of a feather, several hundred times. I've yet to see him venture into mathematics. I mean, multiplication. That usually happens in third grade. But no doubt this would be his first step. He'd say 1 times 1 equals 1. And here is what that looks like in clay and pipe cleaners. Oh, let's get the close-up. Oh, look at that. Beauty. Beauty. So we've got this vertex 1 times 1 brings you back to the vertex 1. Sounds pretty simple. Now, I recognize that the esteemed viewers of this video are probably beyond third grade. They usually don't hold people back for decades, although if that did happen to you, I apologize. The next step for Elmo is, oh, actually this would never be done in the real world, because the real world is real. There's no need for these imaginary numbers, which are actually so difficult that many a postdoc doesn't even know what they are. But kids have great imaginations. What if we saw if they could deal with imaginary numbers? Think about the math for a moment. It's I times 1 equals I. Well, I don't know. That sounds really similar to the last time. Let's see if we can do this with the clay and pipe cleaners. Well, clearly we can't have that 1 at the vertex. So let's knock it off. Knock off its block. All right? And now we just put in a different label here. Oh, this live TV. Internet TV. Oh, this is hard. This is so hard. There we go. Alright, keep the pipe cleaner in there. And, oh, oriented just so. And now we go for the close-up. Okay. It looks pretty similar to last time. Oh, I know. Some math PhD is going to hit me over the head with morphism. I don't understand what they're doing with those things. But how am I getting away with this? Well, it's because the edge here, the edge is the real number 1. Okay? And so that's where the magic, that's why it's so similar. You can go, well, what happens if the edge is no longer a real number? What if the edge is an imaginary number? Well, the math for that is that, let's see, 1 times that I, now on the edge, equals I. Okay, that didn't sound different. But now, how about I times minus I, that gets you back to 1. And so here is, in fact, the graph theory. Oh, I borrowed, got to get my I back. Live TV. It fell on the floor. All right. Oh, yes, down there. We have to place it just so that all of the world can see that here, in fact, is a complex number in clay. Okay? So you can see we've got the 1, 1, a 1 I, an I down here going from 1 I over to I. But to get back, we have to have that minus sign. Pretty sophisticated stuff there. Now, you know, I'm a guy with 2 clay balls here. One that's labeled 1, and the other that is labeled with the I. I'm not a 3 balls guy. So what I had to do was change the label here on these edges, or vas deferens, you know, because these are balls, right? So, okay, there's a pop anatomy quiz, all right? 2 testicles actually are not connected together by sperm ducts. That'd be kind of silly. So please, on your own, draw an accurate picture of this kind of private plumbing. And as a bonus, okay, explain to anybody seeing you answer this pop quiz what you're drawing is at all related to theoretical physics. Good luck. All right, so the real numbers make up these two edges, and we've got 2 imaginary edges, and that's kind of like a complete picture of what's going on with complex numbers. And so I think that's pretty neat. So now we go up to quaternions. So with quaternions, you just need more balls, okay? In fact, it's 2 more balls. And we have the full graph. Oh, right here. Check it out. I, J, let's see, J is up top, K is there. And actually, it was supposed to be like I, indigo, bluish, J, jaundice, yellow, and Kelly green, I was thinking. And we do have 1, 2, 3, 4 little of those loops in black on this thing. So this is the complete picture of a quaternion. Alrighty. So the math, the algebra, I don't know that I want to go through it too much. Okay, you have I times 1 equals I. You have I times minus I equals 1. And then you substitute J's in there, and you into the same kind of relationship. And you substitute K's into there, and you're kind of like done. All right? So let me take a survey of how many people out there have actually built their own representation of Quaternion number graph theory. Now, without collecting any data, I'm going to guess that like it's 0. Like nobody has done that. Because if you have experienced that sort of thing, you'll realize like it's a total pain in the ass. Okay, because particularly to get these, oh great, I can't even pick this thing up. To get these 2 pipe cleaners, there's only like 1 hole, and so you got to take a little piece of string, and you got to tie that little piece of string, and then you got to cut off the extra piece of string, and then this thing like wants to fall apart because it's like really delicate. I mean, you just say, you know, fuck it, I don't want to deal with like two pipes. Oh, and then you look around and no little kid was within earshot Okay, so this is built out of frustration of building the Quaternion graph theory. Much, much simpler. Look, there's straight lines. It's, you know, design-wise. Design-wise. These numbers. These are excellent, excellent design. I like this a lot. Okay. But there's a problem. It's like, well, what are those sorts of numbers? Okay. It turns out that these are formally speaking, the Klein 4 group. I actually like to call them the California representation of hypercomplex numbers, because it's always sunny out there in California, at least compared to New England, and there's not a minus sign in the house. You know, no negativity. It's all about love, making things bigger for all. It's wonderful, wonderful. So, and the thing is, though, that these guys, they sit in my basement, and they actually are the foundation of a belief I have. All right? It's like, the belief is that no matter what pattern of events you construct or you see in nature, on the street, in the LHC super collider, these together, these two sets will describe whatever pattern of events you see. Now the math gets pretty scary, as you can see. There are a lot of pipe cleaners and whatnot, but that is my belief. Okay. Now these Quaternions actually, these have a bad reputation. These have no reputation. Okay, absolutely frickin' almost nobody on the planet works with these. This is like freak show material, all right? These guys, these Quaternions, they have a bad rep, okay? And that bad reputation can be justified, all right? It's not just that they're mean. And the justification is that you cannot represent the Lorentz group with real valued Quaternions. And that one failure is enough to justify people avoiding Quaternions like people avoid people who happen to have leprosy. The thing is that I've actually worked on leprosy, the disease. And one of the few lines of the literature I can quote goes like this. Research over the last 100 years to infect people with leprosy have failed, end quote. And I'm like, much to the great joy and pleasure of the people who were coerced, probably prisoners, to participate in these tests. Oh man. So people, you know, we're just visual. We're not very analytic, you know. We want to believe somebody who happens to be attractive. I mean, lots of news organizations are built on this premise, this observation. Now, leprosy is the most visually damaging disease out there, and I believe that is why it is the most feared. The mycobacteria that causes it actually is no good at jumping from one person to the next. Okay? What we think is that if you happen to be have a genetic flaw and happen to be exposed to this bacillus over and over and over again, then you have a chance of picking it up. So it's only if you're really unlucky and really poor could you get the disease. And then you'd actually have to be lucky and poor to not have it be treated effectively, because actually very inexpensive sulfur drugs do wonders at just clearing it up. And of course it ends up that 2 or 3 million people are that unlucky on the planet. Now last July, I actually did figure out how to represent the Lorentz group using Quaternions. If you have the math chops to understand what I just said, I will leave that as a puzzle at the end of this talk, because after all, it is targeted towards third graders. Now the thing is that that some people will claim that I'm like a Quaternion zealot, you know. Well, you know, full disclosure, I do actually own Quaternions.com. But remember this graph, this is not a Quaternion. And this is just as important as Quaternions are. And so I let this be kind of my defense against saying, you know, Quaternions can do everything, because they can't. So now I'm going to actually do a little sketch of my unified standard model, which is distinct from unified field theory, which traditionally has involved getting gravity and EM together and not worrying about anything else. You better worry about the weak and the strong forces, my opinion. All right. So what you need to do is to get to B squared, the magnetic field, minus E squared, the magnetic field, and E dot B, you know, those things kind of multiply together. And then you drop that into the Euler-Lagrange equation, and out pops the Maxwell equations in the source Maxwell equations, and the homogeneous equations, all kind of automatically. There's a machine that kind of does that. Now, it turns out that if you use Quaternions, that's really pretty easy to set up in a gauge invariant kind of way. And then what I do is repeat the exercise, again in a gauge invariant way, using hypercomplex multiplication. All right? And if you actually try and like superimpose these two in your mind's eye and say, oh, how are these going to be different? All right? You might be able to convince yourself that, you know, half the signs in this one are going to be different from this one, but otherwise it's going to work out. Now, if you give me like 15 chalkboards and 2 hours, I can show you in excessive detail that actually exactly half the equations of Maxwell flip signs. And when you do that, you can spot Newton's law, which is good. That sounds like gravity. And what's cool is that it's got a time-dependent term, so it is going to respect the speed of light, c speed limit that we know exists in the universe. And since you're using hypercomplex numbers to do that, that's also good, because, you know, it's all about love, and gravity's all about attraction. And, you know, all that ever happens in that Hollywood version of California is, you know, everybody gets together and love each other. And, well, gravity works that way. It loves you no matter what you are made of, even down to your subatomic particles, okay? And then what I say is you do this Lagrangian to field equation dance routine a third time. But this time you use both of those sorts of products. And you do it also slightly differently. You make it so that the Quaternion thing actually does depend on a gauge, which means that it can't go at the speed of light anymore. And you do that in the hypercomplex case. Also, no longer gauge invariant, bummer, can't go the speed of light, all right? But you subtract one from the other. And so your gauge dependence of one cancels your gauge dependence on the other, and overall, you have a gauge independent Lagrangian, even though the parts of it are gauge dependent, can have mass, all right? So the Higgs mechanism is a cute solution to this sort of problem, but I prefer acute Lagrangian. I mean, I can actually get Elmo to point to the quantum field equivalence principle in the Lagrangian that you just can't get to with the standard model plus the Higgs mechanism. I mean, people who work on the Higgs mechanism like, stay far away from gravity. It's totally not important. It's not part of their dialogue, as it were. All right. I'm going to stand next to pretty strong statement. That the derivation and the field equations in this unified standard model are drop-dead gorgeous. Now that claim actually already applies to the Maxwell derivation and equations as they are right now. They are stunning. All I am doing is inviting a few more beauties to the party. There are mountains and mountains and more mountains to climb, but at the base is this vision of numbers in space-time made out of clay and pipe cleaners. So good luck in your studies. Oh, I should end here actually with a snarky puzzle. So this is a quote. Quaternions came to Hamilton after his really good work was all done. And though beautifully ingenious, have been an unmixed evil to those who have touched them in any way, including Maxwell. That was Lord Calvin. He was not a fan of Quaternions. So, Quaternions have been a one-trick pony, doing 3D rotations since like the 1850s. We presume that you people trying to solve this little puzzle have gotten a good enough education that you can write it right on down. Say we've got this three-dimensional matrix R, and you want to get it to R prime, and you multiply it on the left by cosine sine I being a 3 vector, times that R, times its conjugate, which is cosine minus sine I. All right? Now, show how, if you substitute hyperbolic cosine for that cosine, and hyperbolic sine for that sine, that evil results. While 2 terms are correct, 2 are missing, and 2 other terms that shouldn't be there are sitting there. I mean, this is ugly. And this is really the first sort of thing that a finely educated simpleton would try. So your job is to unmix the evil. For this not simply connected group, the Lorentz group, find 2 other combinations, of the hyperbolic functions and the R and the conjugates that would correct for these flaws. I mean, that's what not simply connected means. That things are added together. Or didn't they cover the obvious in your group theory training? Now, should you tire of the strain of trying to figure this out, it is available on a preprint server. Just not the preprint server. Since I am living on the ultra-conservative fringe, I have to build my own preprint server out of fairy dust and Drupal. Very old school here. Very preschool, grad school, fringe school, like whatever. All right. Thank you very much.